So I also want to, yeah. So I think the plan is that the first part of today's lecture will focus on pitch control, and then next part more on vibration control. These are two different phases. And then while I discuss things, I might actually refer to some of the papers. I think some of you were interested to know about some of the papers related to some areas, so I can give you a glimpse of those. And then you can take my email if you need more information or a more comprehensive list, and send those to you if you send an email to me. But on my way today, I'll be referring to some of the papers which you have covered. So going back to yeah, so today's first part is on pitch controller. So primarily, this the power, as you know, that is generated in a wind turbine has to be saturated to the rated power. That is really to safeguard the generator. So you know, with this wind speed could be significantly high enough. By now, you know that. Which actually won't be really useful for us because we won't be able to capture the power. And in fact, we are only able to capture the power within a typical range to 5 to 15 meters per second. So anything less or more than that wind speed range is not much of use to us. So, but the most important thing then is that we don't want to actually run the generator above rated condition. So obviously, that is primarily what we want to do. Also, what we want to do is below rated, we want to optimize the energy production. So these two things are mainly done by pitch controller. And as you've seen, when I discussed about this region 2 control and region 3 control in I think the first or second day of our lecture. But we'll look into those a bit more in detail. And then classical algorithms like PI and PID are used, and I've given a glimpse of that as well to you. Now, in addition to pitch control, what is done is a torque controller also can be used either independently or jointly. So these two are the main controllers. Those are actually used in wind turbine. Now, the vibration controllers are relatively new, though most of the companies have been installing dampers in the blade since 2002 or 3 actually, since this age-wise vibration became a problem, and people did see towers vibrating as well. Because of grid fault, actually, maybe not rain, in fact. And so by 2003-4, a lot of patents by the industries like LN manufactured blades, and they had liquid dampers. Vestas had an oil-related mass damper, 2006 and 7. And then when it went offshore, obviously, it was absolutely essential to use the dampers. So it has been using various forms of these liquid dampers and mass dampers in the cell blades inside the blade. Actually, that's where we put the dampers really, because in the nacelle you don't have much space, and you can't put it inside the tower. There's been done 1 or 2 cases where you have put the dampers, but really the blades are very flexible and more prone to vibration. So dampers inside the blades for structural vibration is popular ones, and people have been looking at variations of those. And then as the vibration controllers came, one of the functions of the pitch was also to influence the load, in fact, as we'll see. And they were doing that until 2006-7, between that range, like between the duration 2002 to 2007, when pitch controller was started, and they were being used in the industry. And then subsequently, the vibration controller took off. So load reduction part was then kind of given to the vibration control hardware responsibility, and these two were mainly pitch control and torque control introduced algorithm. So, but you can of course also reduce load by using pitch controllers, as you understand, because if you change the angle of the blade, that will have an impact on the load. We have seen that in calculations. So now also there are higher order controllers for turbine dynamics, which are currently being designed and used, and there are also pitch controllers used to provide damping for lightly damped resonance response of the turbine components. So the gearbox and the tower and decoupling. But also there's another controller which is a power electronic controller, which is actually now taking over in the last few years. And power electronics are now being used to really combat the mismatch between the aerodynamic torque and the mechanical torque, which induces the vibration in the blades and towers. On one side, it also may cause electrical oscillations because of the structural dynamics. So with the power electronics, you can actually convert your AC signal completely to DC and then convert it back to AC. So AC-DC, AC conversion is possible. So you don't have to worry about the impact of aerodynamics and fluctuating wind load and the impact of that on the power quality side. So that's much better taken care of. But on the other side, power electronics controller also are now being used to look at vibration control. So this is like the next sort of development going on. So the initial part was the pitch controller, and then the vibration controllers came in, and decoupling the load control and the power control, and then the power electronics controllers have now been introduced, and more or less all the wind turbines either have something called a STATCOM or a unified power quality conditioner, so they can also be used as well, as we'll see in some examples in the second half maybe. So the main aim for the pitch control then is to design some kind of an optimal feedback control. Now, optimal feedback control is a class of controller, so you can have various optimal controllers. What optimization problem you will solve? So depending upon your objective functional constraints, you can have various types of optimal controller. The way you solve it as well. So you want to basically, as I said, that we want to improve the trade-off between energy capture, actuator duty, and the load, control the power and drivetrain resonances, and mitigate the blade load. So these are the main functions of the pitch controller. And this is a classic PI type of controller, but not in the time domain, but in the Laplace domain. And you can see that this is your integral controller. And if you take the Laplace transform of an integral, then you get 1 over s. The proportional factor gives you kp, and then here you have the derivative, so that's why you get s over here. So those who are aware of Laplace transform, it transforms the time domain response into domain, basically, which converts the differential equation to an algebraic function, essentially. So converting the problem to an algebraic domain, and then solving for the algebraic equations obviously easier, and then design the performance or the dynamics in the algebraic domain to see what the transfer function may look like. Then you can come back again to time domain. So
this case,
sorry.
There's a typo in another.
case in case
Or here. Yeah, it should be KD. So this is the integral gain, this is the proportional gain, and this is the gain associated with the derivative of the state. And for PI, obviously the derivative, constant related to the derivative is equal to 0.
So what is the third aim for mitigation of blade load?
Yeah, so what happens is when the wind is actually coming and hitting the wind turbine, the aerodynamic load is created. Now that aerodynamic load obviously depends on the angle of attack and how the wind is actually hitting the blade. So by using the pitch control, we are changing the angle of the blade. So essentially it means we are changing the drag and lift coefficient and changing the load acting on the blade.
And will in turn reduce the power also.
It will also have impact on the power. So that is the problem. So that is why in one of our work, what we did was we tried to decouple the two and not use the pitch control for vibration control, because obviously load is connected to vibration as well. So by reducing the load, you reduce the vibration, but you also have a penalty to pay, and that is you get less power. So typically, what happens is that if you want to look at a pitch control, then in case of a fixed speed pitch controller, obviously you know the speed is exactly constant. So based on that, you can calculate your rated or demanded power and measured power. So we're trying to saturate the power in this case. So we know what the power we're getting. We know what the capacity of the generator is. and the difference is the error. So if you have less, we can make it more. If it's more, then we have to bring it down. So we use the pitch to make sure that we're always tracking the right power. So why is the pitch demand? And obviously, we want to actually ensure that the integral term ensures a zero mean value. So that means in an integrated sense over a certain duration, you have zero error. And below rated power, pitch varies slowly as a function of average power to optimize efficiency as tip speed obviously varies. And you know the importance of tip speed now, how the power coefficient varies, what is the impact on drag and all these things. So you know it very well, and I know that you know it very well because you answered all my questions. So, and not fully, but to a certain extent. So you have a fairly good idea, I say that. So, so that was the last one was the fixed speed pitch control. So now we are saying the variable speed control. So what happens now is that above rated, the rotor speed is regulated to desired value by generated torque or power is handled. So now we are actually able to also use the generated torque because the speed can vary. So we'll let the speed also to vary, meaning that we'll actually achieve a desired value of generated torque and hold the power constant. In this case, the measured value is the rotational speed of the generator, and we take the difference with the rated speed, and then based on that error, we find the pitch demand. Previous one was based on power when it was fixed speed, and when it's variable speed, it's based on the generator speed. And then what we do is generator torque varies according to control generator speed, and then we fine-tune the pitch and optimize the CP value or maximize the CP value for a given lambda tip speed ratio. So we calculate the tip speed ratio. We know those curves are there, so we can track where the best CP would be. Based on that, we actually change the speed appropriately and get the power. We want to keep the power constant. Now, in this case, obviously, mathematically, we can say that rotor speed is proportional to the wind speed. The speed of rotation of the blade is proportional to the wind speed. The power is proportional to the cube of the velocity. We know now. We know the cube law for power. And we also know that the thrust is proportional to the v squared, or velocity squared, because it comes from half rho v squared, right? So, oh, by the way, one thing none of you actually did was in one of my questions, asked to calculate the power for a, most of it did correctly, almost correctly, 90% I would say correctly, but the small thing none of you actually took account of, and that is for an ideal rotor, but obviously your ideal rotor, that means your machine is a base machine, essentially. You calculated everything, tip speed ratio, and from there you got the radius of the blade, and then you calculated the thrust and the shear, and then applied the lever arm to get the bending moment. So everything is correct. The only thing you didn't do was you took a thrust coefficient essentially equal to 1. You didn't take the thrust coefficient actually as 8/9. Because if you recall, we calculated that the thrust was not equal to 1 actually when it was an ideal machine, base machine. Anyway, that's a minor point. So sometimes you overlook small things like this. So, so the power is given by this expression. So this is the torque, and this is the rotational speed, which is omega times r, obviously, is the velocity, and then this is thrust from which calculated this value, and then Cp. So based on this power, generator torque is calculated. This is a tip speed ratio. So what you do is this is actually your sort of like range 2 control, which we discussed. But these are the generator torque now, plotted against generator speed. So it is slightly different to what we plotted initially, the Cp value or the wind speed. Same curves can be actually plotted as generator torque versus generator speed, and for various wind speeds, you can see. So you can see that the optimal value can be tracked like if it is here, 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 here. So for example, you have an optimal, you want to have a fine tuning optimal operation. So if you're somewhere here, so you continue from A to A1, so you then go to B, so you start producing the power. And then, for example, the wind speed changes. You had 4 meters per second or slightly less than 4 meters per second. And now say you have a value corresponding to somewhere between 4 and 6, say somewhere here. Actually. Then what you do is you know that for 6, this is where your optimal value is. So you draw a vertical line and you get a point of F, which is corresponding to that wind speed. So then from here, you move on over here. Now, normally what happens is that it is difficult to actually exactly measure the wind speed because you don't know what the wind speed is going to be. And then corresponding by the time you change things, there's a time delay effect also. So normally, and you can't change things very fast, high frequency, because that will give a lot of chatter and a lot of mechanical wear and tear to the system, high frequency oscillation. So what you do is, if you look at the next curve, you will have a point G. So you should be ideally somewhere here, but instead of going to point F, you go to point G. So your operating point is this. So it is near optimal then. And then suddenly you find, okay, your wind speed has actually maybe increased, and you're somewhere here. So in that case, you should be at somewhere here, point H. But what you do is operate actually at point somewhere here. So you go along this curve, you'll be somewhere here. And then, say for example, beyond the point where you're saturated. So from here C, your wind speed goes up. So in that case, your point should be somewhere here. So instead of going here, like instantaneously, you go from C to C1, and then if there's a further increase in wind speed, then you saturate the power or torque over here, generated torque. Because your generated torque times the speed gives you the power. Okay? And so if you take a multiplication of this torque and the speed, that gives you the power. So you keep on ensuring here that you have an optimal power. When you're here, obviously you have your generator speed cannot actually increase. You have to operate at that speed here, right? Because otherwise it will be overrated. So that means your torque will have to be saturated here, and this is your saturation torque. To ensure that your torque is here, your speed is here. This is going to actually give you the power of this multiplication of the torque. So this is how typically the control works. So you do not actually exactly track the curve, but you go to the nearest curve possible, like from here to here, and so on. And normally what happens is, with the control system, there's a lookup table which is stored in your control algorithm. So these curves are generated or actually used eventually to track your input. Also, there is a maximum amount of rotor speed, like the tip speed of the blade has to be limited to 70 meters per second for noise consideration. You can't have anything more than that. So other thing I should have said, that the reason also this is done is basically to decouple the torque and the pitch controller, because if you simultaneously use the torque and pitch controller, both will try to optimize, and then you will not have convergence. So it's better to fix one and then optimize the other. So in this case, for example, we are fixing the speed, and then based on the value of the torque, we are optimizing the power. So we are at a speed over here. When you're here, then we actually use the generated torque controller. Or for example, here, what we're doing is So again, here we are actually making sure that when the speed is constant, your torque then is of this value, particular value here. So you're fixing one and then changing the other to get the optimal value. So you're moving from here to here, or you can either move from horizontally as well, like you keep your generator speed constant and then appropriately change the torque in this region. So you do not change the torque and speed simultaneously. You have two things to play around with, You don't change those simultaneously. You hold one constant and then change the other. Get it optimal. There is a control which is called a joint pitch and torque control, obviously, which is what we have discussed so far. And normally above rated, the torque demand is saturated. You know that just now we've seen that the torque error is below rated. The torque error is normally negative. This is where you do the speed control because you're allowed to do that. You don't have a saturated speed. And then you use the integral term, and sometimes we give a bias so that we tend to make sure that the pitch goes towards a finer pitch, and then we can optimize it. So really, it's a matter of how you can in real time optimize the pitch. And also, this integral term helps to prevent the pitch acting in low winds, because if you have a low wind value, then if you use the pitch control, you may not actually get very good effect, because so in our analysis or in our discussions, we didn't actually consider the inertia of the actuator itself, because the pitch is an actuator, and that will actually, so the pitch will also have its own dynamics, you know, that system itself. That dynamics will add to the system dynamics as well. So that has to be an additional considered as well. Now, the impact of turbulence is that if you look at the CP versus delta curve, we have so far dealt with the mean wind speed, and we didn't say anything about the turbulence, but we know that the wind is fluctuating as well. So due to the turbulence, there'll be fluctuation as well. Okay, and therefore, when we estimate certain values like the torque and thrust and so on, we need to actually filter out those fluctuations. Otherwise, what will happen is that you'll be designing a controller, or decisions will be taken based on instantaneous values. And that even though, say, a mean wind speed might be 8 or 10 meters per second, you might have an instantaneous value of, say, 16 meters per second or 17 meters per second. That might be for a short duration. If you design your controller based on that, then you will suddenly have to stop the operation of the generator. But that is not correct, because that only lasts for a very short period of time. So therefore, we use filters to smooth out all this fluctuation. That is why the estimation problem is so interesting, and that's why filters are used for design of controllers. I'm not going into the details of those, but this is actually the logic behind it. As I said, the choice of the controller is crucial, and this is, it's also a matter of research at the moment. And generally, when you're designing the pitch controller or the control systems, you should also take into account the dynamics of the turbine, which is the rotor and the generator rotation, drive rate and torsion. Generator response is very important. Tower for vibration, power, speed transducer responses, pitch actuator response itself, because the actuator also has a dynamics. Description of the aerodynamics, which you have seen, and partial derivative of the torque and thrust, which will, with respect to pitch angle, speed, and rotor, which will actually allow us to apply the controller. Because if you're applying the controller, you need to know if you change the torque or pitch by a certain amount, what impact it will have on various effects on the turbine. So obviously, we need to know the derivative of the torque with respect to pitch angle. How much is the torque going to change if the pitch angle is changed? How much is the torque going to change if the wind speed is changed? Same with the generator speed as well. So, so these are things, and some of these things we haven't discussed actually, because as I said, they are more advanced in terms of control. But trust is an important aspect, and we have considered that, and we will go into a little bit more detail with the tower dynamics coupled with the pitch controller. Because what happened was, this is back in 2002 and 2003 when people did realize that suddenly there was not much of wind actually there, but the towers were vibrating, and they called it flexing. And that's why they were actually looking at it to bring it in the grid code, electric grid code, power grid code. And they found what they found was that if there is electrical fault in the grid, then there's a propagation of that, and that impacts the on the vibration of the tower. And obviously, that means it is not entirely aerodynamic, but it is positive to the overall system dynamics. So, because that was the time when pitch control was also actually gaining popularity, so they actually tried to use pitch control and were successful in suppressing tower vibration by using pitch controller. And how is it done? We'll see very soon, actually. But before that, I should mention also that all these controllers are obviously based on some fancy optimal controller, or could be based on very advanced controllers like robust controllers as well. But robust control means that they work very well for a variety of conditions. Optimal control is tuned to be good for a particular scenario, but it doesn't perform well for all circumstances. But robust control can take into account various considerations and will not work like a optimal controller for a particular optimal case, but will more or less work for various different scenarios. But designing the controller by doing a real-time computation is also very difficult and intensive as well. And time delay is a very difficult thing. So typically, one way to do the control is to calculate all the things and the control gets offline. The curves I showed and the gains I showed, they're calculated offline, the lookup table. So people actually take values from the table and then apply depending upon different scenarios, and then implement the controller. And that is really called the gain sheet. Okay. So I'm not going to the detail of this, but just to give you an idea of what it is. So another thing to mention is pitch control also can be used for stalling, in fact. So what I'm saying is that the use of pitch control for various different things, actually, you can see. So it can be also used for stalling. What it does is the pitch can actually feather out the blade from the wind, and it's kind of cut out, basically. So in the direction of the wind. And as such, then what happens is that there's no torque produced, and then essentially you can put the clutch and the blade can just be free. So there's no stress on the actuator or the pitch as well in that case. So you can use pitch to feather the wind, and basically leading edge into the wind is, so they place the leading edge to the wind and reduce that kind of current to limit the torque. And essentially, this is done when wind turbines are taken out of operation. So a lot of the times, if you notice when you're passing by a lot of wind turbines, you see that it's not rotating, but the blades are somehow kind of feathered out. Actually, in a location, they're just as if they're just static at a particular location, and that is a special position, which is basically it's feathering out. The pitch control is used to do that, and that stalls the machine. Now there are problems with PID and obviously pitch to stall with double values, but I'm not going to go into all these details. I've mentioned about the smoothing problems. I've talked about the different ways to control things. We have already discussed some of these things. And normally what we do is we take the wind speed basically with anemometer reading, but that's, as I said, not presented to a turbine or drift actually. So normally that anemometer reading is used to distinguish between the two wind regimes, low wind and high wind. So it's not really used to measure the wind speed actually. So again, as I said, the pitch control can control the torque, control the thrust, blade out of plane bending. It has a major impact on the thrust, which we'll see very soon, and also the forward motion of the tower. And the relative wind speed of the blade is changed, obviously. But the stability of pitch control is also very important. And people successfully had used pitch control for tower vibration control with the consequence of the tower is low. So the way the pitch control was used for tower damping is actually elaborated over here. So the damping basically comes from aerodynamic damping. And normally we have seen that the forward mode, which is the edge-wise mode, either for the blade of the tower, slightly damped. So the intention is to mainly damp that mode. Now, the way it's done is PID controller with it's called a second order filter. And this is a Laplace transform of the control transfer function. And this is a filter which is designed. And the way it's done is it is actually a resonant controller. So we take the tower resonance frequency and we design this controller in such a way that it will suppress that peak. So if I draw the tower resonant mode, I mean, I think all of you know about the dynamics broadly. So the resonant mode of the tower is say something like this. And if the pitch control has an action of obviously not really applying a load, but it's changing the load acting on it by changing the aerodynamics. And essentially, if you see the pitch control then can be considered as if it is applying a negative sort of load. And the way it is done is that this particular peak has to be reduced. So if you apply a load on this particular transfer function such that this particular peak is suppressed, and you design a filter, something like that. So there's a peak at the denominator over here. So that has to be actually nullified. So use an inverse filter, which is actually then, if you have something 0 in the denominator or close to 0 in the denominator, then you get a peak here. And to combat that, you should have something inverse of that. That means what you have at the top, that actually then nullifies this peak. This is kind of something like a notch controller, and this is actually used to prevent vibration of the tower. Now, to understand this slightly more in detail or intuitively, we can look at the equations, and I'll show you how effectively it introduces damping. So let us look at the tower dynamics again. And let's say this is my equation of motion. And I'm measuring the nacelle acceleration, and obviously this is the velocity and displacement. So either this is the nacelle motion or tower motion, whatever you call it. And then your force is F, and this is mainly the aerodynamic force. So the action of the pitch, obviously I said, is changing the aerodynamic load, right? So then the pitch, when activated, will change the load from F to F plus delta F. Because initially the load was F. If I change the angle of the blade, then the action of that is changing the load acting on the tower. So I've changed the blade angle of the pitch in such a way that the force of aerodynamic force gets changed from F to delta plus. Right? Here?
It could be a minus.
Yeah, but algebraically it's plus delta. It doesn't matter. We'll see what the sign is. Now, if this is the case, then if we can change the force in such a way that it is going to be like alpha minus x dot, then what happens is that this term, when taken on the left hand side, will be actually plus x dot, and will add some damping to it. So essentially, I mean, you can generalize it. I mean, this can be alpha 1 plus alpha 2 x dot, and alpha 2 has to be a negative quantity there. And then when we take that on the left hand side, it will add to this x dot term. So you'll now have damping of d plus alpha. So by changing the load, essentially in some fashion, we can introduce additional damping to the system. And this is exactly what was done using the pitch control to provide additional damping to the tower. So that's very interesting now. So you're controlling the tower of the wind turbine completely by using the pitch control of the blade, and that too by changing the aerodynamic load, in fact, in a way that introduces additional damping. Now, to do this, the only thing you have to make sure that you need to know that what this delta F is going to be. So to find that, let's see what impact the delta F will have if we change delta beta or change in the angle of the pitch. So this is the rate of change of the force with the rate of change of pitch angle. So if I change this by delta beta, then this is actually the delta F. And we have to make sure the force is something like minus dpx dot, which is the damping that will be added to the tower. So using this expression now, we can find delta beta, which is the change in the pitch angle. So this is what we really want to know, because how much is the angle we have to change so that we get sufficient damping. And delta beta is minus dp, which is the damping coefficient that we want to introduce, divided by del f del beta. And this can be actually characterized, meaning that if I apply a certain angle of attack and change it, see how much is the force changing on the plane. If we do that calculation, use that factor, and then obviously we calculate, or we want this dp to be added. So we calculate this coefficient minus dp divided by del beta, multiplied by the velocity that we have measured, or we haven't measured the velocity, measured the acceleration. Integrating, we get the velocity, and then this is our delta beta, and then we change the angle of pitch, and then that will actually change the response of the tower. So this is essentially what was done, and additional damping was introduced. Now there is a catch to it, and the caveat is that if I do not actually apply this value properly in phase, meaning that say there's a slight mismatch, either because of some calculation or because of some fluctuation in the value, or this parameter slightly changes, and when this was supposed to be negative, it now becomes a positive. So even slightly negative becomes slightly positive. Then when I take it on the left hand side, anyway this was very small, damping was not there almost, so that's why we wanted to put some damping. Because you know the difference between zero, no damping, and slight damping is enormous. Because with zero damping, you have infinite response. With little bit of damping, you have the whole thing under control. So at low value of damping, the sensitivity is very high. And when the damping is relatively high, 2, 3, 4%, beyond that, it doesn't matter whether it's 5 or 10%. So it's already taken care of. So now with this phase difference, if we go from plus to minus, we now actually have taken out some damping from the system. So anyway, it was 0, now you're actually adding a value which is negative damping. That might destabilize the system. And this is a problem because we consider it's a problem also with time delay. Because by the time you measure and compute the feedback, obviously the velocity on the left hand side and the right hand side they are not the same. Because you have measured the velocity at time step t, by the time you apply, the velocity is actually at time step t plus 1. So you need to account for that as well. Drivetrain torsional model, like the blade model, you can have drivetrain torsional model, and fixed speed model, and variable speed model. And we have actually a paper where we coupled the blade model with the drivetrain model, and it's a paper published in Engineering Structures with a former student of mine, and Steiner. It's another paper to look at because we did a lot of studies on what is the impact of a grid fault on torsional vibration of the drive. That coupling with the generator is also there. We took a different machine actually, WFN induction generator, and there's a paper in wind energy as well. So those are some of the papers to look at. I can give those references to you. Similar to the pitch controller, you can also have a generator torque controller. And a similar way you can design filters. They can actually have broad-banded and narrow-banded peaks, and then combine the notch filter with this band-pass filters. So these are all kind of how your transfer function has to be designed. So meaning that how you're shaping this section. So for a single degree of freedom system, how do you want this to look like? You can design any arbitrary filter and correspondingly find the load or the input to like look if this is like this and you want to make it something like this. You can do that by using like passive tune mass damper, but you can also do it by using active controllers as well. So you can arbitrarily shape these shapes actually. And if you have a multi-degree of freedom system, your peaks look something like this. And then you can decide to choose filters, and you can shape this to say if you want to be like this, and then this goes like this, and you want flat, you can have some filters. Now, you can't do it arbitrarily, but obviously there's some rules you have to follow, and you can do some kind of you can design some kind of filters to shape this. So this is really what we're doing in a more mathematical way, I would say. But again, to go through this, I mean, to go through a full course on control and design of filters and so on. Finally, I want to show you some results. So what happens when if you use some controllers like the pitch control and the effect on the drivetrain torsional oscillation, for example. So you can see that this is the generated torque and this is the electrical power with no damping. You have a lot of fluctuation here. There's a huge dip, obviously, with the electrical power here. Same thing here. There's a dip in electrical power, but you have now arrested part of the gearbox torque. So that oscillation is suppressed in this particular case. Similarly, for the tower, with no damping, this is what you have, and with tower damping, you can basically suppress the vibration. Now, the upper lines correspond to the displacement here. So you can see the displacement is somewhere between, say, the coordinates of here, roughly 3 to 8, I can say, and this is between 4 to 6, roughly. So consider the reduction as
how does the mean get reduced? Mean value?
No, the mean has not reduced. In this case, the mean is the same for this particular case.
So what is y-axis?
So in the y-axis, there are two things plotted. One is the tower displacement, this one. The other one is the pitch rate. So obviously, because you're suppressing the tower vibration with the additional damping, the pitch is actuated. So you have a lot of high fluctuation in the peak. So pitch demand has gone up. Initially, the pitch was between plus minus 2 degrees, say. Here, obviously, now you're it's still like that range, but you can see visually there's a significant amount of fluctuation in the pitch.
Was it using with the high band pass filter or
In this particular case, I have to exactly see what this is. A paper by Bossarni, 2000. It's in wind energy. I have to see what exactly was done, but I think it was
like low pass filter because vibrations, high vibrations are not good.
well. I think the frequency has not changed much. You can see because if you look at 200 to 50, roughly speaking, 1, 2, 3, 4, 5, 6. And here you have roughly 28 beats also. The frequency is same.
Pitch rate actually gets amplified rate.
The pitch. Yeah.
It actually gets amplified.
Yeah.
What would be the reason?
Yeah. Because so now we have activated the pitch. The pitch is being used to introduce the damping, meaning to introduce the additional force that we need to suppress the torque vibration. That delta. So that is why. So significantly our pitch angles are required. Pitch demand has gone up. Pitch demand. Sorry. Then you can design all sorts of advanced controllers with all these possibilities and combinations. The control blade, tower, all sorts of vibrations, but also generator, torsional drive, and power quality as well. So, and then more fancy controllers like fuzzy logic work by using artificial neural network and machine learning these days to design controllers as well, particularly for wind farms. We are currently doing some work on wind farm. We have a project working. So the two things also can happen. One is the pitch can act individually, or the three blades can have three different controllers, in fact. So individual pitch controller is also possible. That's a more recent one, like only 2010 and 12 we started. So what we're discussing is quite recent, in the past 5, 6, 7 years, what's happening. And again, these are some of the features of individual pitch controller, benefits, and so on. And I'm not going to just read this off, you can read it off, because I'm not going to go. But it won't be possible for me to all the details of this at this stage. And again, I did give these information, but again, to make you understand what happens will take a bit of time. But essentially, what is happening now, beta 1, beta 2, beta 3 are the 3 pitch angles. So the 3 pitch angles will have to be controlled, and there are certain relations between the 3 blade rotations as well. So you could connect the 3 in some form, and then by your transformation, and then design the controllers so that they work collectively or individually. That means all the 3 will have some coordination, or they can act separately as well. This is just a schematic to show how this collective pitch control works with top controller and so on. So I'm going to skip this very fast. And again, you can control the blade bending moment as well, because obviously, you know, if you can feather it out when there's no load at all, and you have a full load when it's facing the blade, there must be some position where you can actually control the load to desired value, and that will change your bending moment as well. This is exactly what we've done. And the effect of individual and collective pitch control can be seen here. So with the collective pitch control, this is the bending moment profile you have, and with the differential pitch control or individual pitch control, you also have additional beneficial effects. Again, similar type of things here. So just to summarize, I mean, pitch control is used for optimal power tracking, but also for structural load reduction. 2 functions. A few classical and quite advanced algorithms were presented here, which are valid or implementable for fixed speed and variable speed machines. But then with the variable speed, you also have the option of controlling the torque. So pitch control and torque control can also work together. And you can have individual and collective pitch controls with various degrees of benefit. And the effect of pitch controller, particularly on tower and drivetrain vibration, is very clear from very successfully. And finally, blade load also gets reduced. Okay, so I think we'll stop here, and the next section is going to be vibration control. So we'll use the next 40-45 minutes to do that, but I suppose you need a break. I need a break. So let's stop here for 10 minutes.
Can I ask a question?
Yeah.
You showed an image with the memo system where you started looking into all 3 blades and their controls. So were there any interactions between, generally when memo comes,
Yeah.
there should be some interactions?
That's right.
And was the interaction positive, or did you really want to decouple out, or what was the status of that?
So if you look at the system now, the blades are coupled to the drivetrain to the generator eventually. So the system you have is a multi degree of freedom system. And your controllers are actually multiple as well, because you have the 3 pitch controllers, you have generator torque controller, it's the 4th one. You can also introduce more electric if you want, but these 4 controls are there. So obviously it's a multi-input, multi-output system. Therefore, your systems are like integrated, you've seen, because if you use the generator torque control, then it has some impact on pitch control as well. They're coupled, they're not completely decoupled. That's it.
Do you want to decouple it? Because when memo system comes, some of the interactions would make it difficult.
Yeah.
So usually in memo systems, we try to decouple it out and make it into CISO systems, make the controllers easier. So if and only if each blade's controls are influencing each other, then only we have to think of decoupling. And only if the decoupling is a negative. If it is positive, then we don't have to think about decoupling.
mean, two reasons here. One is just for the sake of convenience, also we decouple because it's easier to design single input, single output system. We understand the dynamics much better, and then we can go back to the original system. Now, if you look at this system, obviously, a lot of the systems we have discussed so far are time variant, but linear. But you may have also non-linearity here with the current systems, aerodynamic load and so on. So the decoupling may not be easy because then you have to linearize in some way and then decouple actually. So that's one thing. And the other thing is, we have seen, for example, the collective pitch control actually has a beneficial impact here. So you have to take the MIMO system, and then it is not probably that easy to decouple. So we might have to take the whole system together and decide.
You said that tune mass dampers will be certain within the plates. So
They are inside.
How many numbers would be there?
Typically, they put two dampers inside the blade, one closer to the tip and one slightly far away.
For each plate.
The configurations I've seen.
It's already implemented in this field is already applied or
Oh, yeah. There are plenty of patents, in fact, by companies. Last 10, 15 years.
but sir, it will work only at resonant frequency.
Yeah, so
Otherwise it may cause some adverse effect.
yeah, the reason is what they do is they put it for safety reason. They don't put tune mass damper actually, to be honest. They put liquid dampers. And they rely also on liquid damping because the nonlinear damping in liquid dampers are used because they're broad banded, so they cover a range of frequencies. So they do it basically to avoid the situation if there is any resonant situation that they will then cater for that. It's not that they're required for operational reasons.
In TMD case, I found the deflection of TMD in some cases is showing nearly 1 week. Is it possible in that?
Like in terms of the implementation of the PTMT, well, there's not much of space, so that's why the liquid dampers are used.
And in case of liquid damper, most of the people not consider the centrifugal coils in liquid. But it may stick to the other side of it. So will it be implemented completely, perfectly working or in the field? Like if blade is rotating,
Yeah.
Liquid may stick to the other side due to the centrifugal.
Yeah.
So is it perfectly working in the field or like that? Liquid damper.
Yeah.
Did you
Good.
get my question?
No point.
What you are seeing is like you have liquid dampers, so when you are rotating, the
Yeah.
liquid will go down or up.
That's right.
The,
No, into the centrifugal coil.
Yeah.
You always stick to the other one.
Yeah.
You will not like there should be a sloshing. Then only damper will work.
so the centrifugal force, it will stick to the dampers one side. So
Yeah.
will it be effectively working to control the vibration?
What you say is the liquid will not move.
Yeah.
Perfectly.
I can't understand that. When what you say liquid, so centrifugal force is in the normal direction. The liquid is moving in the perpendicular direction.
It's because of
Because
the
of inertia. Because
because
yeah. Yes.
one side.
Transverse direction. Yes.
So in that case, when
Yeah, that will
you give a command for control, will the liquid perform
Got
well?
it. Yeah, these are in different directions.
Yeah. Okay. So, okay, so I think we should come back in 10 minutes if that's okay.
बंद होगा स्टॉप करना अभी ऑफ हो गया
basically some aspects of, like we covered pitch control first session. The other emerging development is in the vibration control aspect of it. And some of these you have seen, and what I'm now going to show is not so much of calculation mathematics, but more on what is being done and what's the focus. So the next 30 minutes or so will have a very fast ride, and so gear up for that and fasten your seatbelt, and we'll have a quick glance there. But okay, so we have seen the structural control. We have seen how blade vibration can control, and obviously offshore floating turbines as well. And these are the problems. Not going to discuss it once again, because more or less all these things we have understood by now. And blade vibrations have major influence on our production, obviously. So that's why it's very important, particularly for the modern day wind turbines. And actually, for offshore wind turbine, it threatens the stability of the entire system. Because if you actually have a blade vibration problem, you're trying to control it with pitch control, and that controller has some delay with your platform motion, the whole system can get destabilized. And this has been actually very recently observed 3 or 4 years back from large offshore wind turbine, when there was some oscillating motion of the blade, sorry, not blade, but the platform, and they tried to actually stabilize it by using the pitch control, but it actually made the thing worse. And you've seen that the motion of the platform is roughly, in one of the cases, 30 seconds actually, was the half a minute was the period. So there's hardly any kind of vibration control device available to control that kind of motion. So platform motion is almost impossible to control. So obviously pitch controller can be used. They used it, but then the problem was it actually made the system worse. Whether because of some kind of base delay, time delay, it's not very well known. So it's still a big challenge. And the next major breakthrough will be when we can actually do something about this. Not with the conventional structure, probably more. Anyway, so we've looked at this, which is the blackwise and edgewise control. We've looked at all the various different things like the centrifugal stiffening, gravitational effects, variable mass and stiffness with the coupled blade torsion, blade tower interaction, retwist of the blade, variation of rotational speed of the blade, rotational sample spectra, power shadow effect. All these are very complicated systems which we can actually account for and solve, and we have done that to a certain extent. And we'll be able to do that if you follow the things that we have done in some of our publications as well. And then we want to see how we can control the vibration. So one of the things we can do is put something like a tuned liquid column damper, and this is actually used in wind turbine blades. And you can see that this is a tube, and you have liquid inside, and this liquid actually oscillates when the blade is moving in the edgewise direction. The liquid oscillates inside this tube, and there is an orifice here. So when the liquid moves, the main reason why the energy is dissipated is because of the motion of the liquid within this orifice. So this orifice is the reason for dissipating the energy. Obviously, that controls vibration. Okay. And if you look at this paper, structural control and monitoring can actually get the details on this. And I think somebody was asking about the centrifugal acceleration, right? So this is of the order of 7 to 9 G. So as pointed out, that the liquid is normally in this position. So that's exactly ideal, because this is where we want it to be, so we can move through this orifice and dissipate the energy. So passive vibration control results give very encouraging results, and you can see that this is the orifice ratio. And if you do vary the orifice ratio, like using semi-active means, you can control the amount of damping and optimize it according to the speed of rotation as well. So here we can see that with and without TLCD, we have a significant reduction in the response. This is without this, with the TLCD. Another variation of this, and this is a paper published in Wind Energy Journal, So here what we did was, instead of that liquid column damper, we used a circular liquid column damper. This is closed, also circular in nature. So the advantage of this is that it is possible to put this in the blade easily, and obviously because of this circular nature, in the previous case, obviously the liquid damper was rectangular in nature. So depending upon the position of the liquid, you might actually go skewed to one side. But here the advantage is that you don't have that problem, because wherever you are, it's still actually within the circular arc of this. So in terms of the construction, it has some advantage. Then it acts like a mathematical pendulum. So it's like a tuning or a tuned mass damper, which is suppressing the vibration impact. And if you then have orifice inside this at various locations, you can actually dissipate the energy as well. And this is, as I said, a paper in wind energy. Look at this, but this also gives you an idea that how we can actually do the vibration with this typical geometry like this and dissipating the energy, controlling the tuning and time real time. Now, obviously, in all these cases, like tuned liquid column damper, tuned liquid damper is also another means to suppress vibration, or maybe a mass device in a kind of circular pathway also can do the same. It's a roller wall damper. We looked at both of these, including some full-scale experimental studies of these damper as well. So the roller damper, this is a paper in sound and vibration, can also have the same effect. Essentially, this is actually the liquid column damper, but maybe a mass portion of that. The advantage of the liquid column damper is that you have less wear and tear, because if you have a solid body like this, moving in a slot, then there's also a lot of impact and friction. But if you're a liquid, that's not there. So liquid will not have a wear and tear that a solid body will have. That's another advantage. This is actually a sloshing damper, so liquid tuned damper. And here we have a tank, which is again located here. And this is a paper we published in Journal of Sound, Fluids and Structures, the fluid interaction here. You can see that so we did a variational formulation, looked at mainly the fluid response here, because the fluid response in this case would be far difficult to model than the previous ones. Previous ones, because the fluid is moving in a tube, it's very well constrained. It's always in a kind of laminar flow. But in this case, you will have liquid sloshing happening. And also you may have breaking of the waves on the surface. This is another type of actuator control which we initially talked about when we were doing the modeling. And the advantage of this is that this is the idea has been taken from aircraft fuselage or space structures. When the space crafts are launched, the launching usually takes place from the east side of the country. Like in our case, Sriharikota, for example. In the United States, it's from Houston. In Australia, it's from Melbourne. So it's always from the west side of the country. The reason is east side of the country. The reason is that when the Earth rotates, if there is a misfire, then the spaceship will actually land in the sea. So that's primarily the reason actually. And the thing is that you cannot actually assemble the whole thing and bring it there. So they have to assemble it near the seashore. And obviously, these are very tall structures, and there's a lot of wind, including gusts coming in. So the way they construct the spacecraft would be, because the people who are working at the top, there are a lot of sensitive devices they have. So they have to control the vibration actually. And they construct a kind of a frame structure, tubular structure like this, and cross structure like this. And the control is done by means of stays or cables. And the cables are controlled by servo motors actually at the end. So the displacement is controlled by the tension of these cables. And essentially, the main platform for construction, which is surrounding the main spacecraft. Actually, the spacecraft is actually in the middle, and surrounding that is a sort of a cross structure where people are working. That actually is controlled by these servo motors. So similar kind of thing has been done here. So this is a active cable tendon. So this is a tendon, and so inside the structure is just a supporting structure. It's not a load-bearing structure. And the cable eventually of that active tendon is connected at the hub or the nacelle. So there's no force actually transferred on the plate because the plates they don't want to touch much. And effect of this is that you can have an actuating force here. Advantage is that this can also control the low frequency zero mean type of response. And actually, in the edgewise direction, gravity is actually a significant load, and including that other low frequency loads are there. So this is quite successful in controlling that particular thing. And that's why this is very attractive compared to any other controllers. And I don't think there's any other controller which actually can do the same thing this one does. I was mentioning about decoupling the role of pitch and the vibration control. So this is a paper we published in the Royal Society journal, where what we did was we proposed a 12 control strategy. And in fact, what was done, we activated the pitch, but also the active tendon control was used as well. So the active tendon control was used to mainly control the vibration, whereas the pitch was mainly used to control the power. And that way we could reduce the demand on the pitch, but also demand on the actuating force on the cable as well. So it's a kind of win-win situation. And in fact, it led to sort of an Pareto-optimal optimization problem in this case. And these are the results. So obviously the control is quite impressive, as you can look, when you can control the vibration well with that tendon. And with the 12 control strategy, we looked at both the out of plane and in plane blade response. So this is actually a case where we looked at the pre-twist of the blade, coupling between in plane and out of plane forces and vibration. And so obviously, you can see that if we have a, say for example, a pitch angle of say 6 degrees or 4 degrees, let's say 6 degrees, and with 6 degree pitch angle, our out of plane response is approximately reduced by 50% when we have an active tendon force. So this is actually the gamma value which is decreasing, meaning the force is increasing actually. So this is the weighting function we have used for optimization. So gamma decreasing means the actuator force is increasing. So obviously the blue is no active tendon, red is slightly less, and then it's the highest value. So obviously when you have a large force with active tendon, you get 90% reduction, but with small force you can get up to say 50% reduction in this case. And what we do now is that we look at the in-plane response, and say for example here you can see that variation with the different loads. Now if you look at the pitch, then varying the pitch we also get a loss in power. Okay? So in this case, say with pitch degree of 6, you have a power loss of approximately close to 40%, 38%. So if you use the pitch control, we're able to reduce significantly the let me just do like whether this is the yeah. So as you can see that when we use the pitch control, we are able to reduce the blade displacement response, but we also have to pay a penalty. And in terms of the power loss, it's actually the graph of the power loss of the pitch. So now let's go back to these curves once again and say that we can reduce the blade response in 2 ways. Either we can increase the pitch angle, or we can also increase the pitch actuator load. So by increasing the actuator load, we reduce the displacement response. But also here you can see with the pitch angle of 4 degrees, we have a reduction of 40%. And if we increase the pitch angle to 10, then we have a reduction of 80%. But then the price we pay is here we have a power loss of 20%, and here we have a power loss close to 75%. Okay. So now we have a choice basically. So instead of actually applying a pitch regulation, we use a combination of the two, and obviously then we don't have to rely entirely on the pitch to do the vibration control. So if we use the vibration control and we do not change the pitch from 4 to 10 degrees, but then you see from here we can actually increase the actuator active tendon load, and we can get the same amount of reduction which we can get with the reduction of the pitch. So from pitch 4 to 10, or say pitch 4 to 8 degrees, you can see that there's a reduction from 40% to almost 65%. But that we can have if you keep the pitch at 4 degrees, but increase the active tendon load from this blue curve to actually green curve over here. So the same amount of reduction is possible that we get from the pitch. So now we have the option of actually not activating the pitch, because the action of the pitch in terms of loss of power is pretty clear over here. And the same applies for in-plane blade response. So you can see, because they're coupled, one will have an impact on the other. So we can also use some tuned mass controllers, but we can't use TMDs because TMDs become unstable. So if you just take a normal tuned mass damper and put it inside the blade, that doesn't work actually. And that doesn't work because what happens is there's a loss of stiffness, and effectively due to the tuning effect, and that actually destabilizes the whole system. So we can use an active tuned mass damper. So that has again the effect of controlling the vibration. So if you have yeah, so it's a figure showing the active tuned mass damper with cable connection here. So now you have a tuned mass damper, a spring and dashboard here. Now there's also one advantage for liquid damper. You don't have to put a dashboard inside. And the blade manufacturers, they don't like a dashboard because there'll be maintenance issue. And you have to replace the dashboard and you rely on the dashboard for tuned mass damper. Then you have to bring down the blade, and that's not easy yet. That's why these sort of devices are not very well preferred. And that's why they prefer to go with liquid dampers. And then there's an active cable here, which is active here. The action of the cable is that when the mass is actually going sidewise, there is a component of the force which is also acting and helping in terms of the control. So it's an active tuned mass damper but with a cable connection. And this is a paper we have in Journal of Sound and Vibration. And you can see you can have significant reduction.
We can also go for undamped tuned mass damper.
No, you can't, because that will destabilize the system. So what happens is, if you take a simple 2-degree of freedom system and a rotating system, rotodynamics, and tune the mass damper to the natural frequency without any damping, then you look at the eigenvalue problem, what you'll find is one of the frequencies basically makes that whole thing unstable. Essentially, there's a rigid body motion. Because of the tuning, what happens? Tuning modifies the frequency of the system, or essentially the stiffness of the system. And if you go perfect tuning, then the stiffness of the tuned mass damper effectively becomes 0. So if you just write down the equations, you'll find that out. We also looked at some soil structure interaction. If there are people from civil engineering here, we're interested to see that how the foundation gets affected by the dynamics and how can you do the integrated system. But and obviously the influence of the structural response, including soil structure interaction, is significant. You can see here, SSI and OSSI. And particularly if you are designing the controller without the soil structure interaction, may actually become ineffective when the soil interaction happens. So you can see that this is uncontrolled and passive in OSSI, or soil structure interaction. Now we have an uncontrolled system. We have a passive TMT here with soil structure interaction. Now, bear in mind, we're talking about when we said that there's a loss of stiffness and instability, we were talking about the blade actually. So far, we have talked about the blade. Now we're talking about the tower. So for the tower, you can actually put a tune bus damper and tune it. There's no problem with that. So only with the rotating system, you have a problem. So it doesn't work. But if we design it according to the passive TMT, obviously it doesn't work. But then we use a controller now, and the controller now is able to actually suppress the vibration, even though we don't have this soil structure interaction included. But that's because active control is a more a better strategy, and actively takes into account the system variation parameters and so on. Moving on to some of the experimental studies and full-scale experimental studies. So this is one of the work we did where we looked at full-scale damper. So this is actually like a damper, and the size is exactly the same that we put in a wind turbine blade. And what we did was we simulated the wind turbine model in the computer, and there was a scramnet controller, and with the fiber optic communication going on between the system here, the physical system and the communication system in real time. So that means as if this is actually in your computational model in real time, or this experiment actually is happening with the full tower integrated with that. Because fiber optic communications have very little delay. And we also do a delay compensation scheme with the controller for controlling the experiment. And we did one experiment with this. There's another paper published in Wind Energy recently, where we actually had put some screens inside, looked at the effect on those screens.
This is actually simulation which we use this input.
This one is a real-time hybrid test. So the computational simulation is going on, and this experiment is going on at the same time, simultaneously. So this experimental system is communicating with the system that will be given to the system as a signal. Sorry?
That signal will be fed to the system as input.
This will be this signal will be communicating with the code itself directly, not inputting it actually. So there is a hardware connection, not a software connection. That's why it's sometimes also called the hardware in the loop. And this is used for say testing of some new elements in aircrafts and automotive systems and so on.
You use the tower model in the computer.
Not the tower model, we use the whole wind turbine model.
You have the real wind turbine model
running, including the gradient. And it's a mechanical system, but we also have an electrical version of that, where we also have the power grid connected, and the power is taken sometimes in real time, and that's called an opal RT. That's also a real time simulator. And the main thing is that the control time delay is not there at all. So what you expect in the field is exactly happening now, because this is in full scale physical tested. All the delays are actually taken into account. Everything is happening in real time.
But you definitely will have a delay because you are trying to do some. Yeah, but when you use a computer, you do discretization and stuff.
So that's why we use a delay compensation. So it's not a normal computer code that you run. So you have to specially design the computer code to take into account this. So we don't use continuous systems. We use discrete systems. something equivalent to what's called in DSP. So all our dynamic systems are discrete systems. So we're not solving actual differential equations. So these are some of the, so you can see this is actually a controller. So this is the controller actually. This is the model where it's being interfaced, and this is your experimental system here. And this is the actuator we're using. This is the damper with the screens. Yeah. So this is what you're saying, like, so your target displacement on set the actuator measured actually. You can see that they're almost accurately matching. This is because we're not using, as you said, not measuring and computing and sending that signal, but we're using the discrete transfer functions with the delay compensation with the controller. This controller is not the controller for the vibration, but the controller for the control of the experiment itself. But you're right, this is an important point. And that's why this is particularly taken into account that this shows that delay compensation is taking place in this case.
We are using which language for coding this one? MATLAB or which computer language you are using? Like MATLAB will be very small for running real time.
So there are various. So this is not a single piece of. So this is not a single platform that you are using. So, so the actuator system is MTS. So the hybrid system is designed by them, and that system they have. So there's a workstation basically, and they have a. So that workstation doesn't do anything else. That's itself the controller actually, and they have written the codes which are in basically C, C++. But there's an interface to that is written in Simulink. So the different levels of interfaces. Then the data acquisition is done using another software which is written by them. So I don't know what's happening. But anyway, to show the results, so this is actually, you can see, I mean, these are not simulated results, these are experimental results by the way. Okay. So oops. Anyway, I think there's some problem. And then these are experimental results, but interestingly, so you can see that the actual analytical calculations we did are now matching pretty well even with the experimental results. So that was very impressive to see. Of course, we did actually choose some, estimated the damping due to the sloshing and the screens, but with that, when we ran our analytical models, found that it's pretty close to what we observed in the real-time number as well. This is actually the suppression of wind turbine vibrations due to electrical faults and grid faults. So as you know that there are sometimes faults in the grid system. And say, for example, by fault I mean there's a dip in voltage. As you have been seeing here, what's happening, the power suddenly goes off. Or there's probably a change in the frequency in the power of 50 hertz or something else. And all this have an impact. And they actually translate to a mechanical vibration problem, essentially. Because what happens is that you see on one side your input is aerodynamic torque, on the other side the generator torque is the thing which is contracting, it's the electrical torque. So if there's any mismatch between the electrical or the aerodynamic torque, there'll be vibration. And this electrical torque is basically getting affected because of the grid fault. So if you do the modeling of the power system, then and induce a grid fault. So this is your power system model here. this is a fax device here, and this is your machine. Actually, this is an FSIT machine. Then the drivetrain here, and all that we have discussed so far actually are over here. So it's a small part of this whole thing. Okay, so there's a lot going on over here. So you can see this is your transmission tower and so on. So there's a wide area network. And obviously, we now look into the impact of this and do some analysis. So this is another paper we published in Wind Energy 2014, the role of fax devices in mitigating grid-induced vibrations of wind turbines. Fax is the full form is flexible alternating current transmission systems. So I don't think you have many electrical engineers or power engineers here, but this is an important element of wind turbines and are being installed in almost all wind turbines. They can play a very important role in of vibrations. So you can see that this is the location where the fault happens. The fault happens for a few milliseconds, actually, maybe 100 milliseconds. That's the time scale. But then that induces large vibration in the blade, nacelle. The nacelle is spectacular. You can see it actually has a non-zero mean part and then vibrates violently. And this is what actually were observed by people in 2002-3. They're concerned about the star vibration, and they didn't know exactly why it was happening, but this is the reason. Now, if you use this device called the StatCom, you can see the red curve now, which actually controls the vibration here also. So it's very successful. In this case, though, the fault duration is 450 milliseconds. Now, this is very important because what happens is the grid code says that, okay, if there's a fault of certain duration and you can override the fault, so get the value of the voltage back again, you can keep on operation. But if you have a fault or dip for more than certain millisecond, then you have to stop the operation. Two things are there. One is, say for example, the fault is of small duration and you electrically override the system, but you do not do anything for the vibration control. And in that case, there is a possibility that the blade vibration and all the nacelle vibration will be quite detrimental to the system, and you might actually have a mechanical failure of the system. So even though the grid code has said and you follow it and override the fault and keep on operating without regard to the mechanical system, then that's not. The other situation could be like if you have a case where your mechanical sensors send some accelerations to the displacement, and you do an emergency shutdown of the plant. And obviously, then you have to be disconnected from the power grid. But again, the grid code says that you have to be connected to the grid code or to the grid for a certain amount of time. And if you don't, then you have to give a penalty. So there's a financial implication to that. So if the fault duration is of a short duration, and if just due to mechanical large vibration problem you stop operation, then there's also financial liability. So controlling this is important from both points of view.
Is there a standard or regulation that could be within time duration? Because beyond that,
The fault.
yeah. Okay, perfect.
Yeah, then you have to stop the operation anyway because of the requirement from the electrical grid code. But obviously, if you ride the fault,
What is the minimum time which we can override? And
so I think it's 600 milliseconds or something like that. And not just the duration, but also what percentage you're allowed to drop, up to 20% or something. But it's all of the order of milliseconds, actually. Because we are talking of all these frequencies here are seconds and so on. And if you go to the offshore platform, it's minutes now. It's a very low frequency oscillation. Okay, so I think we now go into the last bit of the floating offshore wind turbine, which I'll go very fast because we have gone through this pretty much last yesterday. And these are different kinds of devices. We have shown floating TLPs and BERT and a spot type. But I'd like to tell you that actually flutter is becoming very critical now, particularly for the 20 megawatt turbine. The critical speed is going to be close to the flutter instability speed as well. And we've done a work recently published in Journal of Wind Engineering and Industrial Aerodynamics, where we looked at this. So it is basically an instability. It's a torsional coupled instability. So if you do a shell model of the blade and then look at the bending and the torsional mode coupled together, the final model, then and look at the vibration and the control of that, be able to stabilize that. But that is where it is actually critical. This is also known to you. We have gone through these and some of the control. And this is actually one of the papers where we had a passive control of floating offshore wind turbine. We couldn't actually control the platform motions. All we could do was control the heat motion, but the other ones we couldn't. I know people are claiming that they can do it, but it is very strange because it's a half a minute period, so you can't do it with any tube mass temper a little bit time. These are some of the control results where we have optimized the position of the TND and looked at the vertical position of the TND along the spark and looked at the reduction in the vibration, both maximum and RMS values, and works very well in terms of control of the vertical vibration, vessel motion. Also, what we found that the motion of the platform doesn't induce much vibration of the blade because the blade frequency is far away from the frequency of motion of the platform. But obviously, we haven't looked into any instability or coupling instabilities. That can happen because that's what has been observed. Like people who observe the mild vibration, the edgewise vibration from blades and towers, that is what people have observed. So I think it is going to be, so next phase of the work is going to move from vibration control to looking at bifurcation of all these systems.
Only one TMD is considered.
Multiple TMDs. These are some impact on the response. So you can see that this is the cell motion which we have controlled, spar roll, and in terms of references, so this is actually a reference on wind turbine real-time hybrid testing. This is an effect on the wave current interaction. Journal of Sound and Work. This is a mooring cable. This is for pitch control. And this is one new control we have just recently, which is a wavelength-based controller for blade pitch control. So I showed various controls can be used. So this is one of the controls. This is the active tendon control with spinal differencing. And some work on the reliability and spark type offshore wind turbines. And then the soil structure interaction is very important. So there's also paper in structures where we have looked at this. So with the previous references and these references, I think it's a comprehensive list of there's one paper in Wind Engineering Industrial Aerodynamics where we looked at the flutter actually. That is not in the list, but you can look at it. It's published last year. If you need any references or if you need any information, you can email me. Feel free to email me, and I can respond to that. Put the GAN course on your top response, top of the title, and then I know exactly. There's lots of emails I get, so I can screen through those and answer them. Sometimes it takes time. But you know my email, right? All of you.
Is it open in the internet? Is it open if you check it in the Trinity College?
Yeah, my email. Yeah, of course. But also, if you look at the list, probably the Google Scholar, you'll find all the. Okay, so to summarize, I think various strategies we have looked at: active, semi-active, passive, mind control, and various experimental results with hybrid testing. And thank you. So, if you have
the pitch control you have shown, without pitch control, with the active tendon, we can achieve the same. But the case, pitch control we are applying for getting the rated RPM.
Yeah, that's different.
So RPM will change for that we have to change the generator. Because RPM, we maintaining rated RPM
Yeah,
according to the generator capacity.
that's right.
So in that case, we have to replace.
Yeah, pitch control will have to be used because vibration control has no role on the generator control.
So one more. So will pitch control actually reduce
It's only in Vision 2 when you're optimizing the power, you can still do that and control the vibration. Because if you don't do that, otherwise, if you use the pitch control for reducing the load for reducing vibration, then you lose out a bit of power. So this part of the power can be captured by using.
So one more thing you said, generator usually used to change within here like that. So we can change with a more capacity generator. Higher capacity generator.
Defeat yeah, I mean, it depends on, it's complicated because it depends on what kind of warranty and contract you have. So it's not easy to change the generator. I mean, gearbox is replaced quite frequently, and bearings might have to be changed because of damage. But anything for offshore is very difficult. O&M cost will go up actually.
So pitch control will actually reduce the power generated by the turbine. Because even yesterday I saw in one of the graph when the pitch at different pitch angles, the power
Just
just
go down.
So is it mainly to control the damping of the turbine?
No, I said, I mean, as I said, I mean, pitch control has various functions. You know, the list of things I showed. So it's not just one. So it is used. It is primarily used for power control, so optimizing power, and then saturating power beyond the rated zone, and then load control if required. But I mean, that's a few to name. There are other things can be done with pitch control.
Pitch control will actually not increase the power on.
No, because as I said right at the beginning, that we don't need more power. Actually, in fact, the problem is that we have too much of power because you don't have to operate beyond 15 meters per second anyway. That's why you saturate it. So that is why pitch control has a significant role of saving the generator from getting power cut.
If you don't use pitch control, also will be getting reduced power because of vibration. The vibration will naturally reduce power generation.
No, but then see, you can use the stall-induced turbine that used to be done when pitch control was not there. But the problem then is that with stall-induced vibrations, you have separation and vibration of the blades and so on. So you fatigue damage. It's a problem. Without the pitch control. Nowadays, I mean, there are no wind turbines without it. The pitch controller is integral to wind turbines, as all the power electronics. So pitch controller and power electronics will be there even. And then you also have the generator torque controller. So that's why people